So welcome everyone to the final installment of this summer's IPAC. And we're happy to have Swee Hong Chan and Igor Pak giving a series of lectures on applications of the Combinatorial Atlas. So without further ado, take it away, Swee Hong.
Great. Thank you very much for the introduction, Jim. And also, I would like to thank everybody in the audience for coming today. So today will be the first day of this talk for this log concave poset inequalities. So I will present the first 4 days, and Igor will present the fifth day. So I'll be more focused on the technical applications, non-technical sides of this subject, but Igor will be more focused on the philosophical applications, on the philosophical side of the story. Okay. Okay, so the main thing we want to discuss in this series is about log concave inequalities. And here's what I mean by that. So let's say that we have a sequence of real numbers, A1, A2 up to AN. So in this series, these numbers are always real, are always non-negative. We say that this sequence is log concave if for any k strictly between 1 and n, the square of the kth number is always greater than the product of k plus 1 and k minus 1 number. Okay. So in particular, this sequence here is log concave because 9 squared is 81. 81 is greater than 4 times 15, which is 60. Okay. So this sequence here is log concave. Okay. And one of the earliest reasons why people start studying log concavity is that because log concavity together with positivity, they implies unimodality. So this means that the sequence goes up and then goes down. Or like when I told my grandmother about this, like I'm studying log concavity, he said that, Swee Hong, you are studying pyramids. Okay, so in a way that is not exactly wrong. Okay. Okay. And one of the quintessential example of log concavity in combinatorics, it comes from binomial coefficients. So here, n is fixed, k will range from 0, 1 up to n. And this sequence is log concave is because, well, you can simply do direct computation. You take this ratio, you do the calculation, you realize that it's equal to 1 plus 1 over k times 1 plus 1 over n minus k. Because k is by definition between 0 and n, this number is greater than 1. That's why it's log concave. Okay, everything good so far? Oh, by the way, don't hesitate to stop me at any time. Okay. Especially if I like somehow go too fast. Okay. The second example, this one comes from permutations. So let AK be the number of permutations of n elements with exactly k inversions, where inversion of a permutation is a pair of I and j, so that I is less than j, but pi I is greater than pi j. So this means that you inverse the order. That's why you call it inversion. And already, as far as I know, there is no explicit formula for this sequence AK. So you cannot prove log concavity by using direct computation. Instead, what people usually do is that they write the generating function of these coefficients. Then they realize that, oh, what a coincidence. This is what we call the Q analog of n factorials. Okay? And in particular, this polynomial is actually a product of simpler polynomials of the form of 1 plus q up to plus q to the power of I. In particular, this polynomial, the coefficients form a log concave sequence. It's known that this property is preserved under taking product of polynomials. So this property is preserved under convolutions. And that is how we conclude that the original sequence is log concave. Okay. Up till here, everything clear so far? If it's clear already, you can do the thumbs up. If not, then do this. Okay. Thank you. Okay, now the third and maybe the last example for today, it comes from graph theory. So let G be a given graph. Let AK be the number of forests with exactly k edges, where a forest is a subset of edges of a graph that has no cycles. So for example, if this graph is our graph, then this one is a forest, this one is not a forest because it has a triangle. And unlike the first two examples, proving the log concavity of this sequence turns out to be an extremely hard problem. So in fact, it was first conjectured by Mason in 1972. He conjectured it for a more general object called matroid. We'll talk about it later. And this conjecture was, it stays open for a very long time until it was finally proved by Junhe in 2015 as an application of the combinatorial Hodge theory. Okay? And this theorem, and together with Hodge theory, was cited by the International Mathematical Union in 2022 as one of the many reasons behind awarding Junhe with the Fields Medal in 2022. Okay? And today, our goal, for at least will be to give another proof, to prove another proof of Mason's conjecture by using this method of combinatorial atlas. That will be our goal for today. Any questions so far? If everybody is happy, you can. If everybody is happy, we can do the thumbs up and we can continue. Okay, thank you. Okay, so we will start now with talking about what is a combinatorial atlas. And this atlas actually has, I think we will cover like at least 3 versions in this class, maybe 4. But for today, we'll only cover the version 1. So we will go from like a Windows 1, Windows 7, Windows 8, Windows 9, Windows 10. Okay? So it goes up by slightly more and more complex. Okay. But for today, our atlas will simply be a collection of D+1 matrices. Okay. Labeled M0, M1 up to MD. This matrix, the dimension will be D times D. It will be non-negative. So in fact, all of the entries will be counting something. It will be a symmetric matrix. So in particular, this means that all of the, so this matrix is diagonalizable, okay? That all of the eigenvalues are real number, okay? And it also comes with a vector H. This vector will be fixed. We will see what is used later. This vector will also be non-negative, okay? We'll also have some combinatorial interpretation. In general, we will call the M0 to be the parent of the atlas. And M1, M2 up to MD will be the children. Okay? And we'll see how they interact. And the goal of this atlas is always one thing. It's always to prove this property that is called the hyperbolic property, or called the Lorentz property, depending on the literature. Okay? So what is this property? This property says that given the matrix M, take any vector x and take any non-negative vector y. In fact, in our application, both x and y will be non-negative. Take the inner product of M with x and y. So here, this inner product will be the usual real inner product. If you want, you can write this as x m y is equal to x transpose times m times y. Okay. So the real inner product. We say that it has a hyperbolic property if the xmy square is greater than xmx times ymy. And this property actually has a dual form in the form of this spectral property, which is that this property is equivalent to saying that M has at most 1 positive eigenvalues. Okay. Now notice that if your matrix is non-negative, by the parent Frobenius, it has at least 1 positive eigenvalue. So in fact, you can say that eigenvalue is the only one. The other stuff must be either be 0 or minus or negative. Okay, and this property is well known. Like since we can say that it's at least 1920s, maybe around the time of Alexandrov, maybe even before that. That these 2 properties are equivalent. That hyperbolic implies OPE, OPE implies hyperbolic. And we do include a proof. We will not prove it today in this class, but we will actually include the proof in the references, in the lemma 3.5 of the Atlas paper. Okay, for anybody who's interested in seeing the proof. It is a pure linear algebra proof. There's no, nothing scary, okay? Nothing fancy. Okay, and as I said before, that this property is known since 1920s. So naturally, this property has now is like a it's like the fantastic beast in the sense that it's everywhere in mathematics. Okay. Oh, I think there's a question in chat. Let me see what is the question. Okay. Okay, thank you, Anna, for pointing out the references. So yes, this property, hyperbolic property, is everywhere in mathematics. For example, in convex geometry, this is actually used by Alexandrov to prove the Alexandrov-Fenchel inequality, which is this inequality about mixed volume. And in algebraic geometry, this is like is hidden or maybe not so hidden in the Hart-Lefsetz property and the Hotz-Riemann relations in the Hotz theory. And that's very recently in combinatorics, it was used by Peter Brandon and Junhe as a basis for the Lorentzian polynomials. Okay, so this is a very, well, let's say that, a very common property of mathematics. And now I want to say how I want to explain how this hyperbolic property implies log concavity. Okay, and the idea is always goes like this. Suppose that you are given three numbers, ak minus 1, ak plus 1. You want to prove that this inequality, that these three numbers satisfy log concave inequality. What we can do is that first we should try to construct a matrix M and two vector x and y, such that ak will be equal to x times my, ak plus 1 equal to x times mx, and ak minus 1 equal to y times my. Okay. That way, if we can prove that this matrix M actually satisfies the hyperbolic inequality, then it follows that this combinatorial interpretation will imply that this sequence is log concave. Okay. That is the reason why people study hyperbolic inequality, why we used it to prove log concave inequality. Up till here, are there any questions? Okay. Everybody happy? Okay, thank you. So let me continue. So from this observation, it reduces the question of proving log concave inequality to the two questions. First is that the question should be, how should we construct the matrix M to get this number? That is, the second question is, after you construct the matrix M, how do you prove that this thing has hyperbolic property? Okay. The first question is the hardest one to answer, and at least up to now, I don't have like a good answer to that. I think the best answer is like you keep looking at the problem until you find an idea how to solve it, until you find a good good combinatorial interpretation. Of course, these days, some people might say that now that we have this ChatGPT with this AI, maybe they can help. That, so in the future, I don't know. Maybe there is a way for use computer to help this. But for now, it is really kind of like a black magic. So that's for the first one. But for the second, suppose that you already have a good guess what is the matrix M. Then how to prove this hyperbolic property? It can be done in many ways. One of them, and the one that I want to present today, is by using combinatorial atlas. Okay. And as a running example, as a demonstration on how to use it, let us go back to Mason's conjecture. And for today, we will only focus on the graphic case. So in the second class, we will go for the general matroid case. In fact, we will prove an even stronger inequality. But for today, just for we will only focus on the case of graph. Okay. So let G be a graph. V will be the vertex set. E will be the edge set. Okay. Again, AK is a number of variables with exactly k edges. And Mason's conjecture is that this sequence is a log concave for any k strictly between 0 and number of edges. The reason behind this condition is just for formality, because outside of this range, then it's obvious that this sequence is log concave, because the left-hand side will always be 0. Okay. And for today, our proof, our k will always be between 0 and between a number of edges. This is just for technical reasons. Okay. And today we will prove log concavity. In fact, we will prove strong log concavity, which means that I will prove that this inequality is true with this extra constant of 1 plus 1 over k. Which in particular, it shows that this actually, let me put, it shows that this inequality is actually straight. Okay, that there is no equality cases for the normal log concave. Okay, and the way we want to prove it is that I need to define the matrix, right? I need to define the matrix M, right? And to do that, I first need to define this thing that we call the forest word. Okay. Okay. And here a word omega is a forest word, means that this word omega 1, omega k, these are all the edges of the graph. And they form a string, of letters. So this means that the order does matter. And we said this is a forest word if the set omega 1 of the omega k, this is now a subset of the edges. This set need to be edges of a forest. They need to form a forest. For example, let G be this graph. Edges are labeled E1, E2, E3, E4. Here, E1, E3, E2 is a forest word because if you look at the graph, this is E1, E2, E3, E1, E3, E2. This has no cycle, it's a forest. That's why this is a forest word. And by the same reasoning, E1, okay, this is also wrong. This is supposed to be E1, E2, E3. So both E1, E3, E2, and E1, E2, E3 are forest words. What it means is that the order does not matter, but we consider these two words to be two separate words because they are written in the different order. E1, E2, E4 is not a forest. It's not a forest word because they form a cycle. E1, E2, E4. And E2, E4, E2 is also not because if you draw the picture, E2, E2, E4, they now has a parallel edges, right? And we consider that to be a two cycle. So that also doesn't count as a forest. In particular, this means that all your words must be simple, that you cannot repeat your letter more than once. Okay, this is the definition of forest word. And now I use this to define our forest matrix. So for this one, first is that let E be enumerated by E1, E2 up to EM. Okay, so M here will be the number of edges. And my K now that means that its K will be strictly between 0 and M. Our forest matrix has two input, G and K. And it will be an M plus 1 times M plus 1 matrix. It will also be a symmetric matrix. The entries are defined as follows. First is that suppose that I and J are both less than M. So that means that they have an edges that correspond to this number. Then FGK, this will be the number of forest words with exactly with length K plus 1. And it starts with EI, ends with EJ. Okay. The entry when one of the entry is greater than M, so that means that it's equal to M plus 1. This is the number of forests of length K, so the length got reduced by 1. And now it only starts with EI. It can end with anything. Okay, we have no restriction on where it ends. And when FGK, M plus 1 and M plus 1, this is now the word of length K minus 1, and we put no condition on what is the starting word, what is the ending word. This is the definition, and I understand that this can be a bit wordy. So let's look at example so that we have something concrete in mind. Okay, here again is our graph, 4 edges. So this means that our forest matrix will be of size 5. Okay, here K is equal to 2. So now we look at this entry, the second entry, the entry corresponds to 2 entry. This is equal to 2. The reason is that because it counts the number of forest words that start with E2, ends with E3. And the length is equal to 3 because here K is equal to 2, K plus 1 is equal to 3. And as you can see, the only two words are E2, E1, E3, E2, E4, E3. You see that here there's a number 3 here. This is for entry 2, 5. This is the forest word. It must start with E2 because the number is 2. And because it's 5, it means that we have no restriction on the ending. So that's why you see that we don't have any condition on the ending word. And for 5, 5, this is just any word of that length, no condition. No condition on where it starts, where it ends, as long as it's a forest. That's why it gives you 4. Okay. This is the definition of forest word. This is the example. Any questions so far about this forest matrix? Okay. Let me just get something. Okay. Everybody happy? Okay, everybody happy? Then let me continue. And the goal of our goal for today will be to prove this theorem that we call forest matrix theorem. Okay. It says that given any G and any K, the matrix FGK that we introduced from before, this matrix will satisfy the hyperbolic property. And once we can prove this, I claim that this theorem immediately implies the Mason's traffic conjecture in the following way. Okay. As before, let M be our forest matrix. Let X be the vector such that the first M entries is equal to 1, last entry equal to 0. Y is the opposite. First M entries equal to 0, the last entry equal to 1. Okay. And now, if we look by definition of this X, M, Y, let me just do the calculation now in the. By definition, X times My, this should be the sum of, sorry, let's do XMX. This should be the sum of I and J equal to M of the FGK, of the sum of FGK of entry I comma J. Right? This is a definition of this is using a definition that M is a forest matrix. This is equal, oh sorry, this is I and J starting from 1 up to M. This is equal to the sum of a number of forest words link K plus 1 starts with EJ, starts with EI, ends with EJ. Okay, sum over all possible value of I and J. This is the same of simply of the number of forest words of length K plus 1. Okay. But now remember the forest word is a forest word if it's just an ordered ordered version of forest. The length is K plus 1. So this means that there is a K plus 1 factorial, ways of ordering them. So this is equal to K plus factorial of number of forests with K plus 1 edges. Okay. And that is how we get this equation over here. That XMX is equal to K plus 1 factorial times AK plus 1. By the same reasoning, XMY become the K factorial AK, YMY equal to K minus 1 factorial times AK minus 1. Now you plug in the hyperbolic property, this K factorial, they all cancel, and that is the reason behind we get the constant 1 plus 1 over K. So in hindsight, you can think of this, the fact that all of this, not just this one, but many other log concave inequality, the fact that they are actually has this constant 1 plus 1 over K, it actually suggests that you should look things as a word, not just as a set. Okay. Up till here, everything happy so far?
Yeah, I have a small question. Is that
Yes.
is the inequality like straight, or in this case like actually will equal?
That's a good question. Like, can this inequality be strengthened? And the answer is yes. This inequality is always strict. It's always strict here.
I see.
And we will see that actually the right constant to be put here in special case, actually you need to multiply by, let's see, you need to multiply by 3 over 2. That'll be an extra constant. And that I think we'll cover, I think maybe next class, how this constant can be improved to the level of 3 over 2.
Okay, thank you.
You're welcome. Any other question? Thanks for the good question. No question? Okay, then let us continue. And so, okay, so now we have seen that the Mason's conjecture can now be reduced to prove this Forest matrix theorem. That we want to prove that this matrix actually satisfy hyperbolic property. Oh, by the way, I just want to mention that one common question people ask whenever I present this part is that some people will ask, like, what is the connection to matrix 3 theorem? Which is saying that the number of a spanning tree of a graph is equal to the determinant of the Laplacian matrix. And then the natural question is to ask that, is there a combinatorial interpretation for the determinant of this matrix? And unfortunately, so far I tried several examples. I tried several times to find a combinatorial interpretation. It seems to be the case that there is simply no meaning for the determinant of this matrix. Okay. But other than that, are there any other questions? No. Okay. Thank you.
Can you say for which graph these inequalities are tight with the factor?
With the factorial, or that will be for a cycle graph. And that is for the case when k is equal to number of vertices minus 2. In all other cases, it's actually not tight. Thanks for the question, Ron. Okay, if there's no question, then let me continue. Oops. Okay, so we will so now that we have seen that Forest matrix theorem can prove Mason's conjecture, let us now prove this theorem today. Prove this Forest matrix, and we'll do that by using the atlas method. Okay, and to do that, I will need to define an atlas that's called the Forest atlas. Okay, here is that. To do that, first I need to define what is the edge contraction. So given a graph G, the contraction of the edges E of the graph is the graph G over E, where endpoints of the edges E are now merged into one vertex. So for example, here is the graph G. The red vertices here, the red edges here is the E. Then G over E will turn these red edges into a loop and will turn these edges here into a parallel edges. Okay. And so usually when people do this thing, they often say that we will remove the loops and remove the parallel edges. But for today, for technical reason, the loops and parallel edges are not removed. This is so that there is a bijection, there's a natural bijection between the edges of G and the edges of G over E. This is for a technical reason that will be important in the definition of the atlas. Okay. And with that, let us now define the atlas. To define the atlas, we need to fix T. T should be strictly between 0 and 1. This is again for technical reason. D will be equal to n plus 1. Remember that D is the size of the matrix. Remember that the Forest matrix, the size is n plus 1. That's why this D is equal to n plus 1. K will be strictly between 2 and number of edges. So notice that this is also equal to m. The reason why I don't start from 1 rather than 2 is because the case k equal to 1 will be the induction case. That will be the trivial case. And the case k greater than 2 is the harder case. That's the one that we will prove by using atlas. The Forest atlas is given as follows. M0, the parent, will be equal to T times FGK plus 1 minus T times FGK minus 1. Okay, so it will be an interpolation between FGK and FGK minus 1. The children, whenever I is less than m, is always be FG contraction EI. So it will be a smaller graph, and the K becomes K minus 1. So not only that the graph becomes smaller, the K minus 1 also become lower. Okay, and MD, which is like the last children, this will be equal to FG K minus 1. So no contraction, but the value of K minus 1 also goes down. And there's a reason for that. The reason is that always that for this kind of question, you want to go from something complicated to become something more simple. So the parent will always be the more complicated one. The children will be always the simpler one. Right? It's a bit similar to how families are. You know, you see that the parents that turns out usually are the one that is more stressed about life, while the children, at least when I was a kid, is the one that's happy Life was so simple, right? Okay, and our h here, which is our vector, the first m entries will be t, the last entry will be 1 minus t. Okay, and the goal of at least our plan to prove this forest matrix is to show that all of these metrics here satisfy the hyperbolic property. And then after that, if you take t equal to 1, you take the limit as t goes to 1, then you solve the Forest matrix theorem. Then you get that this matrix also satisfy hyperbolic property. That is our goal. Okay. Up till here, is everybody clear with the definition of the Forest atlas? Actually, let me get some water. Okay, if everybody is happy, then let me continue. And in general, if you want to directly prove that all of these metrics has hyperbolic property, it will be really hard. Instead, what mathematicians usually do when you see problems like that is that you try to break them down into smaller properties. Break them down into properties that's easier to verify, and in the end, we'll still prove the hyperbolic property. That is what we will do. We'll introduce some properties that's easier to check, that somehow when put together, magically, the hyperbolic property follows immediately. Okay. Okay. Let us first discuss the first two properties. The first property is what we call the irreducible. And this is a property, this property is satisfied if the matrix M0 is irreducible. By irreducible, I means that this is equal to saying that the matrix M0 cannot be written as a block matrix of this form, where it's a blocks and everything below the blocks are all equal to 0. This is what is called reducible. So this means that we don't want our matrix to be of this form. Okay. And by the way, this will only apply to the matrix M0. Only the parallel need to be irreducible. The children can be reducible. In fact, in most situations, the children must be reducible. It actually has a lot of 0 rows, 0 columns. Okay. The second property, which is what we call the H positive, this is the property if our H, so all of the entries are strictly positive. Okay. And this true property is, sorry, maybe are there any questions so far about these properties before we go for example? Okay. So these properties are immediately satisfied by the atlas, by our forest atlas in the following way. First is
Sorry,
that
I was a bit slow.
no problem.
This irreducible, yes, this irreducibility, is this kind of up to permutation of rows and columns, or is this just as the matrix is, you should not split?
Good question. Yes, thank you so much for spotting my mistake. Yeah, I think I need to put that after permutations of rows and columns.
Okay, thank you.
You're welcome. Thank you so much for pointing to my mistake. Yeah. Okay. So let's see if our atlas satisfy this. And of course, answer spoiler, yes, they do. First is that for H positive, notice that I define we choose the T to be strictly between 0 and 1, right? That is how we know this vector is strictly positive. And for the atlas, to check irreducibility, we will, without loss of generality, assume that G is simple. So this means that G has no loops or parallel edges. In that way, you see that given any two edges or given any edges, you can always find a forest that contains these two edges. This is in particular, what we call the exchange property for forests. That implies that all non-diagonal entries, so the diagonal entries can be equal to 0 because they are because you cannot have parallel edges. But otherwise, the non-diagonal entries are always positive. In particular, that implies that the matrix FGK is irreducible. In particular, and if you add some other positive matrix to something that's already irreducible, it can only be more irreducible. That is how we know that M0 is irreducible. That's how we check the first two properties of the atlas that we need to have. Okay. Up till here, everything clear? Okay. Next step.
Yes, a
Uh,
question. This depends on K, right? It depends on the maximum size of a spanning forest. Doesn't it?
That's a good question. It depends on the value of K. If K is too big, then this matrix will be zero matrix. And that is why in our proof, let me go back. Our forest matrix theorem, let us go here. We see that we assume that our K is strictly between 0 and 0. Our K is strictly between 0 and E. This is exactly for this technical reason. Okay. Thank you so much for whoever is asking this question.
But still, I mean,
Yes, what's the,
uh,
yes? What is
I
the
mean,
question?
the size of a maximal forest or spanning tree could be much less than the number.
That's a good question. So, okay, maybe I should add this for every connected graph. Yes, thank you so much. So, we need actually more. Sorry, yes, that's a good question. I forget to
Again,
say that.
take the complete graph. I mean, the maximum size of the forest is n-1 and
Oh,
and the number of edges is n choose 2.
that is a good. Sorry, this is a mistake. Less than V. Yes.
Thank you. Thank you.
Yeah, thank you so much for the stopping. Okay, so I guess that I also need to change the many other things, but yes. So in all of this, like this K is always equal to V. Okay. Thank you so much. Any other question? Any other typos? Okay, so the third condition, which is what we call the decreasing support. This is saying that the support of the children should be less than the support of the parent. So in a way, this is saying that the children must be less complicated than the parent. Okay, and here a support of matrix is the index such that it has non-zero. It has a non-zero entries. Okay. And for this property, again, the forest atlas satisfy, because remember that all non-diagonal entries of FGK are positive, right? In particular, that implies that the support is equal to the whole set. They're equal to D. And because this is the M0 is a sum of FGK with some other positive matrix or some other non-negative matrix, it implies that the support of M0 is equal to D. And for MI, the children, we don't know what is the support. It can be equal to D. It can be a bit less than D, but it's always the case that it's always less than the whole thing, right? You cannot have more support than the whole set. That is how we know that this forest atlas satisfy the decreasing support. Okay. Any questions so far for this one? Okay. Thank
Will
you.
excuse me, will the ordering of these children play a role at some point? Or so far it seems to me that this is irrelevant, but will this like be important later?
For the forest, no. Let me correct. I said for today, no, but in the second class we will talk about equality condition, and in that case, then the order does matter, because there are some of them some of them will be more important than the other. Let me just quote Animal Farm here. All of them are equal, but some are more equal than the other. Okay. Sorry. Okay, thank you so much for the question. Any other question before we go for property 4? Okay, so property 4. This is saying it's called transposition invariance. It says that let MIJL, this is a ZL entry of the matrix MI. It says that this index IJL can be permuted in any way. So MIJL should be equal to MJLI should be equal to MLIJ. This is in philosophical or in a sense, is saying that your object is more or less commutative in some way. This property, by the way, in version 1, this is a property only in version 1. In version 2 or version 3, transposition invariance will be replaced with something more complicated but more general. This is because matroid by nature is commutative. But if you go to some more complicated object like gridoid, or you go for poset where things are non-commutative anymore, this property won't hold. Okay, and by the way, so for Forex Atlas satisfy this is because of our combinatorial interpretation. Because the entries of MIJL will be the forest words. So depending on where is the you put IJL, it means that your EI will be put in the beginning, your EJ will put in the end. But remember that this forest is a permutation, right? No matter how you put the ordering does not really matter. If you change the forest ordering of forest word, it will still be a forest word. That's why we can, in particular, say that put the EI, EJ, EL at the beginning, and these three numbers are all equal to this number of forest word. This is where we use the commutativity of the matroid. We use the commutativity of the graphs. Okay. And finally, the fifth property is also actually the most complicated property. It's called the inheritance property. So far you see that our properties, they do not have a connection between the parent and children. This is where they get connected. This says that the ij entry of the parent is equal to the j entry of the ith children after you multiply with the vector h. This is the property that tie all of the matrix, the parent, the children, and the helper here. Oops. Yeah, the matrix is as a helper. Okay. And by the way, this is the last property. After this, we go we will have something more fun. So for last property, this is verified. Unfortunately, the only way to verify this is by doing calculations. This is the following. The ij entry of M0 is by the definition of forest matrix equal to the t times the ij entry of FGK times 1 minus t of the ij entry of FGK minus 1 by definition. Then by definition of forest word, this is equal to forest word of this form, starting with EI and with EJ. The first one will be a word of length k minus 1. The second one will be length of k minus 2 because of the difference in this index. And now here is the important step, which is that you see that any word, forest word of G that start with EI, they correspond to the forest word where you remove the EI, but now you evaluate it with respect to metric with the graph G over EI, with the contraction of G with respect to EI. This idea, you can argue it goes back all the way back to TAP, where you use this to define the dilation contraction for the TAP polynomial. Dilation, contraction, recurrence, right? And after that, you use this definition, you do the same calculation again. You notice that T is equal to H, entries of H when I is less than M, and 1 minus T is equal to the entry when equal to M plus 1. Then you redo the calculation, like the one from the previous slide. You see that by definition, this is equal to G entry of Mi times H. So this is how you verify these 5 properties. And don't worry, everybody, this is the last property. Okay. Now, once you have this 5 property, here is how we use them. This is what we call the children to parent principle. The idea is this. Suppose that you know that M1, M2, MD, all of them satisfy hyperbolic property. And you also know that your atlas already satisfy these 5 properties that we already verified. Then automatically, it follows immediately that the M0 is also satisfy the hyperbolic property. In a way, I like to think of this as like like it's a bit like COVID, where if you have you have all your children, they all maybe got COVID in the daycare, they come back home, all of them got COVID, and then 3 days later, the parent also got COVID. That is how this children to parent principle work in real life. But in mathematics, here is how we will use them. Our strategy becomes much simpler now. So first is that you verify this condition, the 5 condition, the one that we do from the previous slide, then we do induction. By induction, we will say that, okay, maybe we will look at the very simple case when the matrix is hyperbolic, is easy to check, maybe by direct calculation. Then from the simpler case, you put all of the simpler matrices to be the children. Then these simpler matrices will, by the children parent principle, will tell you the parent will have this property, then the grandparent got it, then the grandparent got it, until everybody in the family tree got the hyperbolic property. That becomes our strategy to prove the Forest matrix theorem. Okay. In fact, let us just go immediately to the proof. Right. So recall that what we want to do again is that we want to prove that this matrix FGK satisfy hyperbolic property. When where is my for any k strictly between 0 and v. And we'll now give maybe 2 slide proof. So first is that let k be equal to 1. This is the simplest case. And we talk a lot of generality, assume that G is simple. When G is not simple, there is a way to reduce this question for simple graph. Then when G is non-simple, you notice that this matrix is equal to this matrix. All the non-diagonal entries is equal to 1. All of the diagonal entries except for the last entry is equal to 0, while the last entry is equal to 1. These entries, you have 2 choices, actually maybe 3 choices. First choice is you do the calculation yourself. Second is that you ask your student to do it. Third is that now you use the Wolfram alpha to do it. And for me, I choose the third one. I use the Wolfram alpha to do the calculation. They pop up these numbers. The first one is certainly a positive number. The next few ones are minus ones, so they are negative. The last one is the d minus 1 minus d minus square plus 4. This is something around minus 2, right? Sorry, minus 1, but a little bit bigger than that, like minus 1.1, depending on how big your d is. In particular, this means that this matrix has at most 1 positive eigenvalue. And by the equivalence that we know, this matrix satisfies the hyperbolic property. So that proves the induction case. Now assume k is equal to 2. Remember that by definition, mi, m1 up to md, they are fg over ei of k minus 1. So by induction, all of them satisfy the hyperbolic property. Then by the children parent principle, M0 satisfies hyperbolic property, and M0 is equal to this matrix, right? Now take the limit as t goes to 1. It is easy to see the hyperbolic property is a property that is an invariant undertaking limit. And that is how we conclude that the matrix FGK also satisfies the hyperbolic property. That proves our Forest matrix theorem. Okay. And in conclusion, sorry, before we proceed further, are there any questions about the proof? Everybody happy? Okay.
Yes, a question in the contraction. You do have loops, right? A loop, it's just one loop.
Yes, when you do contraction, you always have loops, and that is why. So this is a detail that I skip, which is the word Vittor's law of generality, because actually there is you need to do some linear algebra to reduce the case from the loop to the case of non-loops. But basically, the idea is that we have loops. The row and columns that correspond to the loop will be equal to 0. And the hyperbolic property, it remains the same even if you remove the 0 and the 0 rows and 0 columns. That is how we reduce it to be the non-simple case. That's how we reduce it to the simple case. Sorry. I hope this answers your question. Yeah, so there's a bit more. The proof is a bit more technical than what is presented. Any other question? Okay, everybody's happy? Okay, so in conclusion, what we have shown today is that we have proved the Mason's conjecture for the case of graph. That we have shown that this number, the sequence A1 up to En, they satisfy what we call the strong log concave property. Okay. And now now let me go back to the question by Anna, which is that, is this the best we can do? Can we actually improve? And the answer, quick answer is, yes, we can. In fact, we can prove a stronger inequalities for a far more general object. And that is, in fact, the original question of Mason. Mason actually asked the question not just for graph, he asked the question for matroids. Okay. So a matroid M, this is you should think of it as a ground set, as something with two input, a ground set X, and a subset of independent set that is called the subset of the ground set that's called the independent set. And in these independent sets, they need to satisfy two properties. But before I say the property, let me just present the graphical. Let me just present two examples. The first example is graphical matroid. This is when X is the set of edges of a graph. The I here will be the set of edges that form a forest. So this is our example from before, when you have forests. The second example will be realizable matroid. This is a matroid where X is where the ground set is a finite set of vectors over any field F. Well, I will be, pardon the pun, the independent set will be the set of linearly independent vectors. That's actually why they are called independent sets. Okay. And this matroid needs to satisfy two conditions, the subset property and the exchange property. What the first property, it says that given an independent set, the subset of independent set is again independent. For example, if you have a forest, any subset of forest is again the forest, because if you don't have a cycle, you remove an edges, you cannot form a cycle by removing an edges. The second property is called the exchange property. It says that if you are given two forests, one has more edges than the other, then you can move one of the edges of the larger set to the smaller set, and again you get the forest. Okay. So this two property, it might sound a bit abstract, but the idea is that you should think of this as the abstract version of linear algebra. That this two property is actually a property of linear algebra, maybe even the only important property that gives you basically everything that you need. Okay. And the Mason's conjecture is given in the form of 1, 2, 3. I presume this is because at that time they are not even sure that the first one is correct. That's why they hedge their bet, like 1, 2, 3. But the conjecture is that let Ik be the number of independent set of size k, where if when your matroid is a graph, graphic matroid, this is the number of forests. Then the conjecture is that it's log concave. Second conjecture is strong log concave. The third conjecture is ultra log concave. Okay. And for a very long time, we don't know how to prove this, unfortunately, until it was finally, let me just explain. Sorry, I go too fast. Let me just explain why is this constant here, 1 + 1 over k times 1 + 1 over n minus k. This constant is actually equivalent to what we call is actually the ratio of the binomial coefficients. And this, what it is saying is that if given this number, you should think of it as the probability that given any subset of size k, that your subset is independent. So it also have a combinatorial interpretation. Okay. And this conjecture was actually solved in for 50 years. There's no progress until it was finally solved in like 3 years. The first person who actually the first big breakthrough was done by Adiprasito-Hurkacz, where they proved that yes, this sequence is log concave, and they did it by combinatorial Hodge theory. Okay. Second breakthrough, almost in the same year, was by He, Schroeter, and Wang, where they proved that yes, the strong log concave is true. So this is the one that we proved for forests. Okay. And they prove it again by using Hodge theory. But rather than doing it directly to the matroid, to the number Ik, they first prove this thing that is called correlation inequality. And at the end, that proves after some calculation, that proved the strong log concave. And finally, maybe like 2 years after that, it was proved independently by Anari, Liu, Oves, Garan, and Vincent, and also by Brandon and He, that this sequence is actually satisfy the ultra log concave. And the proof is already a bit different. They use Lorentzian polynomials which is like a slight like a modification of Hodge theory to prove this theorem. Okay. And at this point, okay, sorry. What I want to say is that at this point, some of you might ask, right? Okay, Swee Hong, maybe is this the end? Like, can you actually give a stronger inequality after you see this? Surprisingly, the answer is yes, we can. It actually has an even stronger form. And just like any user, if any of you like to watch the Marvel movies, they always like to, like before the end of the movie, they always like to say that next episode preview, just to make sure that you come for the next episode. So I will do the same thing here, and forgive me for doing it, but I will not tell you what's the improvement for now. If you want to see the improvement, please come to the next class. Okay? But I can okay, I can see some people unhappy. Okay, so let me be a bit evil. Sorry, let me not evil. Let me make some concession. Next episode preview, we will show, at least for the case of graphic case, that this constant, and also you need the k to be equal to v minus 2. When k is smaller, the improvement will be a bit different. But for the case of k, the improvement will be from 1 over n minus k will become 3 over 2. And this is actually a real improvement in the sense of asymptotic improvement, in the sense that the Mason can only give 1 when you take the limit as the number of edges goes to infinity. But this improvement actually gives you 3 over 2. Okay? And this bound will be proved by Atlas in the next class. So I guess that I should end this with thank you very much for listening, and I hope to see everybody again in the next class.
Thank you so much.
Thank you so much, everyone.
Any questions? Yeah, I actually have just one small question. How do you decide when you see like a problem and then you want to use the tool, the combinatorial atlas? How do you find the parent and children and also the age?
That's a good question. How do we usually guess this? How do we guess the matrix?
Right.
So in a way, it's a bit like a try as hard as possible until you get the answer. But there is usually some tips, which is that let me go to the forest matrix. Where is it? Yeah, usually the idea is that you try from something that's simple first, which is that try when case k is small, like when k is equal to 1. And in that case, things to be usually simple enough that there's like not so many rooms for you to guess, right? It's either doesn't work at all or you actually find something that possibly works. In that case, you just guess that, oh, when k equal to 1, your matrix actually is this simple form, right? And from there, you guess that this is probably the right matrix, because this matrix actually has everything you want. It has a combinatorial interpretation. It also has the eigenvalues is correct, that it has a hyperbolic property. Then from there, you try to guess like what should be the more complicated version. Sometimes you guess it wrong, then you give out on that route. You guess something new one, and you just keep going until you get it correct. And it's a bit like I think I forget who said this, but it's like in chess, one mistake is all you need to win your whole career. But in math, one correct guess is all you need to prove something. And I think that is the idea that is my answer for this question.
Right, thank you.
You're welcome.
Any other questions? All right, if not, then let's thank the speaker again.
Thank
For
you
the
so
next
much. See everybody the next Tuesday, right?
Yep, so I will see everyone on Tuesday, and make sure we come to the great talk because we already watched the preview of that, right?
Thank you.
All right.
Thank you so much for the advertisement.